ray. So the I here represents the incident ray, and the R here represents the reflected ray. So at this point, I is equal to R. The incident angle is equal to the reflected angle. Let's see what we have here. The bouncing back of a wave into the same medium when it gets to a boundary. Bouncing back of a wave into the same medium when it gets to a boundary. It could be irregular reflection or diffuse reflection, depending on the nature of the surface. So if the surface is smooth, the reflection you get becomes regular, call it regular reflection. But if the surface is rough, you now see the result of it. So this may end up producing a blurred image. We call this diffuse reflection. So let's look at this other figure here. Still the same thing as the first one here. And this represents incident ray, the reflected ray. And this is the normal. So we have theta 1, theta 1. That is to say that the angle of incidence is the same as the reflected angle according to the law of reflection, which states that the incident ray, the reflected ray, and the normal all lie on the same plane. So the incident ray, the reflected ray, and the normal all lie on the same plane. Okay. Let's quickly go to diffraction. This is an introductory class. We are not expected to really go deeply, but in our next class, I think we'll pick some of these topics and then we try to break them down accordingly. Okay. We have diffraction of waves. Diffraction of waves. The bending around of wave when it gets to a boundary. Okay. The next one here is refraction of waves. Refraction of waves. Refraction means refraction of wave is the change in speed and direction of waves when it moves from one medium to another medium of different densities. So you now see the incoming ray and the refracted ray. So this is the first medium. This is the second medium. This is the angle of incidence. This is angle of refraction. So this is angle of incidence, I. Incoming ray, E. Refracted ray, R. So you now see that there is a change in speed and direction at the second medium, medium B. That is to tell you that medium B is denser than medium A. What I mean by being denser is thicker, it's heavy. So you can see from the figure. Let's look at the next figure here. They still explain the same thing. So you see the direction of travel of the incident ray, and then the refracted ray. You see the angle. So this medium here is less dense than the second surface. Okay, so if light travels from a less dense medium to a denser medium, it tends to bend towards the normal. So this is the normal. You see that this light bends towards the normal here. But if light travels from, look at the arrow here, these are not the same figure. So you see the arrow here representing incident light, refracted light. Look at the arrow here telling you that this side is the incident light and this side is the refracted light. So you now see that when light travels from a denser medium to a less dense medium, it changes in speed and direction and it bends away from the normal. So when light travels from a less dense medium to a denser medium, it bends towards the normal. But when light travels from a denser medium to a less dense medium, it bends away from the normal. That's what that figure is telling us. From this figure, we can see. Okay, let's go to laws of refraction. We've said that refraction is the change in speed and direction of a wave when it moves from one medium to another medium of different densities. Okay, now, laws of refraction. Number one, the incident ray. I'm coming. Okay, laws of refraction. Number one, the incident ray, the refracted ray, and the normal at the point of incidence all lie on the same plane. The incident ray, the refracted ray, and the normal at the point of incidence all lie on the same plane. The incident ray, the refracted ray, and the normal at the point of incidence all lie on the same plane. Okay. The second law states that for two given media, the ratio of the sine of the incident angle to the sine of the refracted angle is a constant. I come again. For two given media, this one and this, or this one and this, or let's consider this. This one is water and this is glass. This one is A and this is glass. So those are two different media. The law states that for two given media, the sine of the incident angle. Okay. So the law states that for two given media, the sine of the incident angle, the law states that for two given media, this sine of the law of refraction states that the second law of refraction states that for two given media, the sine of the incident ray, the ratio of the sine of the incident ray to the sine of the refracted ray is a constant. Okay, so this was discovered by a Dutch physicist by name Snell. Wilbert Snell. So from the laws of refraction, we have it that sine I over sine R gives us a constant which is called the refractive index. The refractive index does not have SI unit. So the first equation, we have that n equals to sine I all over sine R, equation 1. We can as well define refractive index as the ratio of the velocities. So the velocity of light in the first medium all over the velocity of light in the second medium gives us refractive index 2. We can as well compare these two also. All right. So the first equation we have here is that sine I over sine R gives us a constant, which is refractive index. And then this one, the velocity of light in the first medium all over the velocity of light in the second medium gives us also refractive index. So there are cases where the angles were not given, but the velocities were given. You won't say, oh, because you were given velocity, so you can't find the refractive index as well. Okay. We also have it that n1 sine I equals to n2 sine R, where I is the incident angle and R is the refracted angle. And then the N1 here represents the refractive index for the first medium. And then the N2 here represents the refractive index for the second medium. So assuming we have this to be N1, our N1 here is 1.33, our N2 here is 1.50. And then we have the incident angle to be 60. So if you are asked to find the refracted angle R, all you need to do is to do a simple substitution. I'm with you, still with you. Okay. Okay, so from the figure, we have that N1 sine I equals to N2 sine R. We also have that our N1 is equals to 1.33 into this. Don't forget that this n subscript 1. So don't be confused about that. This n subscript 2. The same thing is applied here. For the sake of time, I will not be able to look for certain things. Okay, so N2 was or is 1.50, and our I, the incident angle, is 60 degrees. Okay, 60 degrees. And we have to find R. Okay, so by substitution, we now pick in place of N1, which is 1.33, we now put it where we have N1. So here we will have 1.33. The next thing here is sine. We have sine here. Sine I. What is I? 60 degrees. You know, replace 60 equals to, from the formula, equals to, then N2, 1.50, 1.50 sine R. Okay, so the unknown here is R. We have this, we have this, we have this. We are looking for R. So we are going to divide both sides by 1.5. So we will have that 1.33 and 60 all over 1.50 be equals to sine R. But it's not proper keeping it this way. So I'm going to lift this and then I bring it to this side. So okay. Hope you're still with me. What do I do now? That's sine sine R equals to 1.50 33 times 68 over 1.50. And we are going to make the subject. So we remove or divide both sides by sign. We will now have inverse sign this value. So say R equals to inverse sign sine inverse times the power minus 1 into this 1.33 times 60 all over 1.50. Then there's the bracket. This will now give us R equals to inverse sine inverse sine 0.7679 0.7679. When you press sign, inverse sign of this value using your calculator, you will have R equals to 50.1 degree. You can try that by yourself. In the course of doing that, you will get a better understanding. Okay, so what's the final answer to that problem? Oh, all right. Okay, so this is the answer. Let's go ahead. This one says, if light travels from glass to A as shown in figure 18.2, I mean this figure below, then we use the expression. So from Snell's law, we have it that N equals to sine I, the incident ray all over the refracted ray. Now, we are saying that if the light is traveling in from a denser medium to a less dense medium, then we are going to simply say sine x. So in this case, look at the x here, sine x all over sine the refracted ray is still the same as the other one. So always look at this figure. It's very necessary. So the velocity also, velocity in the first medium, Vx, all over velocity in the second medium, Vy. Okay, all right. We move to the next one, total internal reflection. Total internal reflection. So I think you can see clearly the figure here. This is a prism, and this is a light source. We now see the incident light here being incident on this prism at a particular angle. Look at here, if you have, look at here, you have 0 degrees. This one is 0 degrees. Then from here to this other point is 10, 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60, 70, 80, 90. The same is applicable to this side, 0, 10, 20, 30, and all of that. So this light that is incident on this prism is at a particular angle. And at that particular angle, you now see that the light is reflected totally. So at this point, one may say total internal reflection has occurred. We are going to understand what we mean by total internal reflection. The figure we have here is similar to the drawings we are seeing here. So this figure here, this figure is the same as total internal reflection, this diagram we are seeing here. Okay, let's come back. You now see this. These are two media. The first one here is glass, and the second one is air. This a denser medium. This one is a less dense medium. What happens when light travels from a denser medium to a less dense medium? It moves away from the normal. You remember, I have said this before. So the alpha here in this case represents the incident angle, and the beta here represents the refracted angle. Now, you see reflected rays here, but it's very weak. It's written here. So some of the rays of light do reflect, even when refraction occurs, but it's not strong. Okay, so at this point, one can identify a particular angle here. You can measure this angle and tell somebody what it is. Now, if this angle is increased, like we have here, assuming this angle was 20, then you now decide to increase it to 30. That's what you are seeing here. So if this angle is increased, what you observe is that the ray of light that travel from the the refracted ray will also move close to the boundary here. So the more you increase the incident angle, the wider the refracted angle. It gets to a particular angle whereby if you increase the incident angle, all the ray would fall in between the two media, which is the glass and the air. So at that point, you have the refracted angle to be 90 degrees. Where you have the refracted angle to be 90 degrees, you call this particular angle of incidence the critical angle. So what is critical angle? Critical angle is simply the angle of incidence in the denser medium when the refracted angle in the less dense medium is 90 degrees. Let me go down so that we stay with you. Critical angle, the angle of incidence in the denser medium when the refracted angle in the less dense medium is 90 degrees. The angle of incidence in the denser medium, this angle, when the refracted angle in the less dense medium is 90 degrees. At that point, you say that critical angle has occurred. So here you still have the weak ray, and then the refracted ray is now running in between the glass and the air. If we increase this angle further, let's assume that the critical angle was, maybe call it 63. If we increase it, the incident light beyond that angle, say 63, now increase to 50, as we have seen here. All you will observe is total internal reflection. So you now have a bright light here. It will not be as weak as it was before. And all the ray, the incident ray, will reflect totally. It reflects totally instead of refracting. Okay, so that takes us, to our next definition, the total internal reflection. What is total internal reflection? Total internal reflection is the reflection of an incident ray of light at the interface between the medium of incidence and another medium of lower refractive index when the angle of incidence in the denser medium exceeds the critical angle. Total internal reflection is the reflection of an incident ray of light at the incidence between the medium of interface and another medium of lower refractive index when the angle of incidence in the denser medium exceeds the critical angle. Okay, so I still have another question here for you. Remember this expression. Remember equation 3. Equation 3. N1 sine I equals to N2 sine R. N1 sine I equals to N2 sine R. So at critical angle, we replace, instead of I, we now put C. We now put C here. So let's look at the C here. That C represents critical angle. So at critical angle, the refracted angle in the less dense medium is 90 degrees. Sorry. Please don't forget, at critical angle, the value of the refracted angle is 90 degrees. So you can see in place of I here, now replace this, place of R, replace 90. Sin 90 will give us 1. So we now have that n sin C equals to 1. So we can write this expression as n sin C equals to 1. If we are to make n the subject, then we will have that n equals to 1 all over sin C. And if we are to make C, sin C the subject of C, we now have that C equals to 1 all over n. Okay, so at critical angle, these equations hold. At critical angle, you have that's all this. If C is given, we will use this to find the refractive index. And if N, the refractive index, is given, we will use this expression to find C. So let's assume that we have something like this. This is the normal. This is the critical angle C. Okay. All right. Let's look at this one here. So N here is 1.50, 1.50. All right. And you are asked to find the critical angle. All you need to do is, remember this one here has 90 degrees, the refracted ray here. So this 90 degree, everything here has reduced to 1. You now have 1 over n. So the n here is for the denser medium up here. So all you need to do is just to continue 1 over 1.5, 1.50. 1.50 is still the same thing as 1.5. When you divide 1 by 1.5, you have sin C equals to, let me check my calculator. 1.50, 0.66, 0.6 7. At this point, since we are looking for C, we will now say C equals to inverse sine of 0.67. With you can as well try it and check what will be your answer. 0.67. Then you have 42 degrees. So that is the refractive index, if this were to be your question. So that's how to calculate refractive index. Let's go back to the main screen. Okay, study question. Before I get to that point, I think I've seen a figure here. This is glass, this is water. I would like you to solve this problem. The answer is 63 degrees. Just try to see how you can solve it. Then we move down to the study question. What is the critical angle for light traveling from water to air? The refractive index of water to be 1.33. What is the critical angle for light traveling from water to air? That's the question. Okay, so we are asked to find the critical angle, but we have been given the refractive index of water. So if we use equation 5, you try that by yourself. This is equation 5. This one is given 1.33. So you will now substitute that 1.33 into n, and then let's see the subject the same way I have done the other one, and then check what your answer would be. You can even drop a message there on the comment section. So let me try to save time. Applications of total internal reflection. Applications of total internal reflection. Where do they use total internal reflection? You see binoculars. These binoculars are astronomical telescopes. So this is an example of prism binocular. This is the human eye. This is the telescope. It makes use of total internal reflection. You will now see the prism inside. See 1, 2, 3, 4. Okay, so you now see the prism inside. When light travels from this way, look at this is the objective lens. When light travels from here, reflects totally until it gets to the human eye. Reflects until it gets to the human eye. So one application of total internal reflection is in the construction of the prismatic binocular telescope. We also apply it in what they mean by periscope. Periscope. You see the figure of periscope here. What's a periscope? It's an instrument or a device used to view distant objects. Maybe if you have an obstacle blocking you like a mountain, in the case of a going for a battle, like you are in the war front and you intend to see what is ahead of you, then you can make use of this. You see one prism here, look at another one. Here's a rays of light from the object will now reflect totally until it gets to the eye of the viewer. So this is periscope. Look at it very well. It does not make any use of lenses. There are no lenses here. It's only prism that you see in a periscope. In case you see questions like that, which of the following instruments do not make use of lenses? You should know the kind of instruments. A periscope uses prism. There's no lens here. Okay, let's go to the next option, optical fiber. Optical fiber. So this is an example of an optical fiber. It's a cable. This cable has an outer jacket strength member. It has coating. It has cladding, and then the core. This cable works under the principle of total internal reflection. I think that is how far I can go on the introduction to waves. I think that is how far I can go on this topic. So please, if you enjoyed my class, if you enjoyed this session, please, I just want you to subscribe to our channel in order to encourage us to do more. Just click on the like button and also share. This is Supreme Online Lectures. Supreme Online Lectures. So this what you will see. Just drop a comment on the comment section. When I come to online, I will reply your messages. Thank you very much. Thank you so much. I really appreciate you. Have a wonderful day.